Okay. Yes, come in. Everyone is welcome. So, topic today, sample complexity. So remember from the introductory lecture, there was half space classification and one nearest neighbor algorithms. And we said that, okay, qualitatively, one nearest neighbor looks very good because it can fit any hypothesis or any true classifier, but we need a lot of samples. So what we care about is how fast the error decreases of a learning algorithm when we give it more data. And so this, we will start the discussion now. And the topic is called sample complexity. So how many samples do we need to get a reasonable bound? Okay, so now we did online learning so far. Now we will do batch learning, more or less normal setting, except that we will now assume that there exists a true classifier, a classifier that is always correct. So we will speak about realizable setting. So most courses, they go directly in the setting, in the agnostic setting for machine learning, but then the probability is much harder. And then they do a difficult chapter where they have a low noise regime and do the same result as we start with, but a little bit more general. But then I personally, I don't like this for an introductory, I mean, for when we just start. And also we have people from theoretical computer science, they care a lot about this realizable setting. So there is even a second reason for it. Okay, but you don't care about all this motivations. So let's just start with the model. And so what we will have is we will have a way to sample inputs from somewhere. And we assume there exists a true classifier. And we also have a learning algorithm. So sample complexity, what we first need to do is say what we want. And after we know what we want, we can think how to get it. I mean, it's general principle in life. So let's first say clearly what we want. And so we want a learning algorithm so that if we sample inputs from it, we run the algorithm, it trains it, we sample inputs, we ask for the teacher for the true label, the supervisor. So it's called supervised learning. For the true labels of these samples, then we can run the learning algorithm, and then we get a new classifier. So of course, the learner doesn't know what is the input distribution and what is the true classifier, but it gives us hopefully a good approximate of the true classifier. And then we will sample a new input and check whether our prediction, our approximate classifier gave a good prediction. So given, so let us define what is the risk of a classifier. And so we have given two things. We have an input space X and a measure P. Measure P over X. The first thing, and a classifier H from X to Y. And so we will always assume Y is equal to 2. And X, we always assume non-empty. And so, yeah. And then the rest is, I forgot the notation I'm using. Oh, there is no notation for risk. So the risk of another classifier, it's just the probability when we sample an input from P that f of X is different from Y. So this is the easiest risk for binary classification. Okay, But this is just the risk of a single classifier. What we really want is like the average risk over training. It might be a very easy target to state. So what is this average risk? So let me remind how I call this. Oh, it doesn't have a name. Just say the performance. Right? So let us fix some notation and some procedure. So first we generate training set. And so we will generate the set containing training samples. And N will always denote the size of the training set. It's the plan for the course. Then we ask for the labels from supervisor. And so I will use SH. So again, we have a measure P. And so we have the same two things. And the true classifier, the supervisor will give us the labels. So we will have X1, H of X1. X10, H of X10. So now we have a training set. Now we can run our the learner. Sorry, run learner. And this will give us a classifier denoted Fs of H. So it's classifier mapping from X to Y. And then generate test point. And so here we generate from Pn. So we generate test points independently, which is very important assumption in our model. We get the training points independently, and then we get the test point. X also from the same distribution. So this is crucial. Training and test points are generated in the same way and all independently. And then our performance measure is probability over these 4 steps that our prediction is correct. So we are interested in probability. And so over S from Pn, X from P, and the learner might be randomized. But we require that this is a deterministic function. So the probability that SH of X is different from H of X. So this is the most basic performance measure one can dream of or imagine or define. Well, if you know an even easier one, let me know. Okay, so there are 3 sources of randomness in this probability. There is randomness in generating the training set. This is just a deterministic step. So we fix measure and H here. Then the learner can have internal randomness. Then we generate the test point. So 1 and 4 are the steps. So randomness of learner is implicit in this probability. Okay. So since we are working with, okay, let's do a little example. So I first consider so let us do a little exercise. So the risk, so let y equal to 1 and 2, and let us consider the constant function fi of x equals I. So we let us consider 2 functions, the 2 constant functions, f1 and f2. And then I claim that risk of f1 plus risk of f2 is equal to 1. So this is first exercise. Is it clear why? And so this is probability that f differs from 1. and F differs from 2. They're two disjoint events, and they happen surely. Okay, this is easy observation. So that means that at least one of these two classifiers has risk at most 1/2. So it's very easy to come up with a learning algorithm that produces something here equal to 1/2. So for example, the learner that ignores the training set and just picks a random label and outputs the constant function. So this is not interesting. However, if we get the risk very close to 1, we're also happy. And so imagine that you have or 0.9 or whatever. We just invert the labels of the produced function. Okay, so that is what we should remember. Let me check what else I have to say. Let's do a little example. So let us evaluate this measure for one nearest neighbor function and use the domain -1, 0, 1. It's a simple exercise. And let the true function, okay, so P is uniform. And H is equal to absolute value. Right, so it is 1 and 1 on these 2 points and 0 and 0. So what is this quantity for this example? Sorry, we also have to fix n here, the size of training set. Oh, we have here n for 2 points. When we use 2 points for training, we draw them uniformly over, so with probability 1/3 over each of the 3 inputs. Okay, and so there are many cases, but there is only one case. So we have many possible drawings of the training set here. And so it can happen that we have two times the same input. So the training set can be 2 times 0. And this is bad news because then the nearest neighbor algorithm will output a constant 0 function, right? The nearest point will always be the middle point that has label 0. So true function of -1, 0, 1. So that's our true function. Okay. So, and this is the only case that our learned function makes 2 mistakes, that we have risk 2/3. In all other cases, we will have risk 1/3. So can you check it? So there are the cases where we have a coinciding training set. And so when we have 2 times -1, risk will be 1/3. When we have 2 times this, also the same. And when we have 2 different points, then nearest neighbor is right on these 2 points from training set and wrong on the other point. So we can evaluate this measure. So there are 9 possible sets. And so this measure, let's call it star. So we have star is equal 8 times 9, so 9 cases where we have risk 1/3 plus 1/9 where we have risk 2/3. And so now we can evaluate it. I mean, it's not so important. And 10, 20 is that. So it's just example to get in touch with this.
So can you hear me?
Yes.
So you write the star on the left side of the board, and
so this is our performance measure, but it depends on P, H, and N. So we want it to depend on N because we want, for increasing data, see how the performance improve, but we don't want it to depend on H and P. So first proposal might be to define performance measure by taking supremum over all classifiers and all measures P of our learning algorithm. And now we will see that this will be a big problem for us if we do this. So I claim that if we take supremum over all the classifiers of this performance measure, then our performance measure will be optimized by just algorithm that remembers the training set and answers consistently and answers whatever outside. So for this, to prove this, we will use lemma. Let me remove it because we will need the lemma a few times later in the lecture. And so lemma says that for every x, for every p, for every n, so there exists a classifier h from x to y. Okay, yeah, if I say for every x, for every y of size 2, but it's clear, right? It does not important how we choose y. And so there exists this probability of this measure s over pn, x over p, probability that f as h of x different from h of x is bigger than e and p over 2. And what is this? E and P is just probability that the test point does not belong to the training set. So this E, probability that test point, and E, probability X not. Let me write it like this: 1 minus E and P divided by 5, and so then we have X. So E is probability that we are in the training set. So let's write it in the same way as in the lecture notes. Okay. So what does it mean? It means that if our sample space, if X is a huge set, usually it's exponential in the dimension and the dimension is huge. So if we sample a few points, then if S the size is small, so of course S has size n, X also from P, yeah, then the size is small and probability to find a point in the training set is exponentially small. And that means that there is always a function H that does not better than probability 1/2 than the trivial learning algorithm. So if this is our objective, then some trivial learning algorithm is the answer. So it's not a good objective. That's why lemma is important. So and our plan will be to restrict the set of classifiers. But that was the same story when we spoke about online prediction, right? We also said if we take all classifiers, then our mistake bound is stupid. Okay, so let us prove the lemma. So the plan is to use probabilistic algorithm. So we will fix a way to generate hypothesis and then say that expectation over the hypothesis of this probability will satisfy this inequality. So we will say that expectation of probability that f as h of x not equal to h of x is bigger than 1 minus okay, let's now write it probability x not in s times 1. Okay, and so now I must say how we generate h. And h will be random function. So whenever we need an input, we will assume that it's the label of h is randomly generated over the two labels with probability 1/2. Okay, so now let us try to prove this inequality with this procedure to generate h. So let us first fix a training set S. So then let us look at probability that f s of h of x is not equal to so fix s and x not in s. So then the probability over generating h that these are different is exactly equal to 1/2. Clear? And so we fix a training set of size n. And we fix an input not in the training set S. Then probability over picking h. So since x is not an S, this value is independent from other values of h picked. So we have probability 1/2 here. Okay. So what does this mean? That when we take x randomly, so let's now not fix x and look at probability of this condition to x being not in the set S. So it's also 1/2. So now I pick x randomly and a condition on this event. And so it means that probability when I remove condition yeah. So let us now look to the probability that this happens and this happens. Then I claim that this probability is at least 1/2 times probability that x is not in S. It's kind of morning. This is actually equal, right? What's happening here? So it's conditional probability times A and B. Probability of A given B and B times probability of B. Okay, so that it falls with inequality, with equality. Yeah, my brain is not working now. But if I drop this, then it becomes inequality. And so probability that prediction differs from h and we are outside the set is exactly equal to 1/2 times probability that we are outside the training set. Okay, and so it means that if we drop this thing, this condition here, then probability can only increase like this. So I'm just using that probability of A is bigger than, it is very logical. So that's what I'm saying. Okay. So, and that's precisely what we need, except that we have fixed x, and we are no longer fixing this here. Go to. Okay, is it clear on this point? I was a bit confused myself, but it's kind of elementary, right? So first we fix s and x outside. Then we conclude that probability on probability that prediction is wrong is 1/2. Then we take random x and we condition on the event. Then we still have probability 1/2. Then we remove. Then we look to the conjunction of this probability. So we have exactly 1/2 times probability of condition. And then we look at the inequality. Then we draw this part. So probability of one part of the end can only be bigger than the conjunction. Okay. So and then we are done. This is for fixed s. So when we take for a random s, it's also true. And so it's for, since it's true for each s, it's also true for randomly generated s. Oh, we remove this one. And now we use that expectation of probability as the same as probability. So here h is inside the probability, here we have expectation, but that's the same thing. And then we apply probabilistic method. If expectation of something is bigger than something, then there must be some, at least one h for which this is true. And this finishes the proof of this lemma. And so the some people call it no free lunch theorem. And then there are many variations of it, but always the same proof. So I don't bother to read. I once read such a paper and then decided not to bother with any of these discussions, because just saying if you generate h randomly, you will do no better than remembering the training set. Okay. Yes. So that means that when we want interesting performance measure, we will also fix a set of classifiers and then check what is the best learning algorithm for this set of classifiers. For example, half space list. Okay. So then okay, so now our question changes to what is a good set of classifiers? For what set can we make this thing go to 0 when n, so the supremum goes to 0 when n becomes large? But okay, so so let us now define a measure that works for a whole set of classifiers. And so now let us have a new definition. Our performance measure will be supremum over h in a set of class. So h is the subset of y over x. So this notation is not used in the notes, but maybe you used it in other courses. This is a set of functions from x to y. So you could also think about it as lists of length cardinality of x. But okay, x can be infinite. And so our performance measure is, so when we fix the training size, we look at supremum h in our class and measures p over x. Over x. And then we look to the same probability for generating a training set and a test point that h of x is not equal to h of. Okay, and we can say that the class H is good when we take the limit over n, and this goes to 0. Then we can say that our class is learnable on average. So when we have enough data, our performance measure becomes arbitrarily small. So it doesn't exist. I just made it up for introduction of this lecture. So, but I will say H is learnable on average. I mean, I made it kind of up, but it's also useful and improves this notion. So for sample complexity lower bounds, then usually this compact notation really helps. Okay, and so now we could think what are good classes and what are bad classes. So for example, if H contains only one classifier, then so we say H is always non-empty, so I don't write this. Okay, so the smallest is one classifier. So then this should be a good classifier, right? So what is learning algorithm that creates zero error? So learning algorithm will just always ignore the input and always output this single classifier in H. So learning algorithm here, it receives SH and it must output a classifier. So always be the single classifier. Other examples. Another one is imagine that H contains two classifiers that disagree on every input. So they're different on each input. That's G, and then for all X, f of X differs from G of X. And then the learning algorithm is also easy, right? It just, as soon as it takes the first point, checks the label and output the corresponding classifier. If they're always different, it can identify it from one point. Okay. So, so here this probability drops to 0 as soon as n is at least 1. So now the second thing is, what if there are two classifiers? Just general two classifiers. On some inputs they're equal, on some they are different. So then it's also learnable on average. So how can we prove this? And for this, there is like a little story. So there is a picture. It's in the slides. I will add it in the notes when I add it. So there is in the Middle Ages, there was like a king, and it was common for kings to be friends and also to poison your friends. So so it's time. So in these times, it was normal to poison political opponent, and so you can. So if a king, imagine that the king receives a whole bowl of candy, and so if, received from friends. So king has a dilemma: should he eat from it? And so he has food taster, and he says, "Please eat a random candy." And then wait a few days to see whether the food taster dies, and then the king can eat one candy. Let's say that he will eat one from the bowl. Okay, so now what is your chance of dying? Because political friend also knows that king is scared and he will not poison all the candy in the bowl. Oh, there is some question, but I guess camera a bit left. That is not the right left, but I will use it backwards. Yeah, thank you, but you should make some sound next time.
Can you hear me?
Yeah, I can hear you. Yes.
Yeah, I asked you a question like a couple minutes ago, but you didn't hear me. Maybe you should turn volume.
Yeah, it was a bit soft, but it's strange I didn't hear you. But now it's louder, so I should be able to hear you.
Yeah, okay, thank you.
Yeah, and otherwise call me on Telegram, then my phone will go off. I always forget to switch off the sound on my phone. So, okay, yes, there's a important. Okay, yes. So we have candy. So we have a big bowl of candy, and some of them are poisoned because opponent knows that poisoning all of them is not a good strategy. So, and so the king, he will take n candy randomly and then give it to the food tester. And if they don't die, he will eat one of them. And so I claim that with this strategy, chance of king dying is at most 1 over n plus 1. So you can do even a little bit better, like some exponent 1 minus 1 better or something like that. But that's not important. So let's go for the bound 1 over n plus 1. So how does it work? Well, let us pretend that instead of drawing n candies here and 1 for eating the king, let's first draw n plus 1 candies. And then from these n plus 1, let's take a random one that goes to the king and the other ones so there is one for king and the others to testers. Okay. So then there is only one situation. When we look to this n plus 1, there is only one situation where the king might die. It is when there is precisely one poisoned candy among this list of n plus 1. Right? And by the equivalence, like taking n and then taking 1 is the same as taking n plus 1 and then randomly select the 1 for the king. It's the same. And so the king can only die if there is precisely one candy of n plus 1 that is poisoned. And then the candy for the king is precisely this one poisoned candy. So chance of king dying in this process is 1 over, at most 1 over n plus 1, regardless of the fraction of poisoned candy here. And this is the proof to say that this is the proof to say that any set of 2 classifiers is learnable on average. So lemma, if h equals 2, then h is learnable on average. Okay, and so proof. So what is the problem in this? What is the problem here to prove this? So we have 2 types of inputs. So inputs where the 2 functions f and g agree, and functions where they disagree. Our only chance to make a prediction mistake is that in the training set, all the inputs, there are only inputs where classifiers agree, but on the test set, the classifier disagree. That's the only way that we can make a mistake. So poisoned candy means classifier disagree. And good candy means classifier agree. So if we have good candy for testing, we are fine. And so we know that this measure, we know that supremum over h in fg of this probability of making a prediction error fh over x not equal to h over x is smaller than 1 over 1 plus n plus 1. So do I need to write? That's clear, okay. Yeah, so also online people. So it's an important point, so you need to say something. Okay. And we can actually extend it. If H is finite, then this is also true.
So, and is the number of x's?
Yeah, so what we then do is apply the union bound. And so we look at each pair of functions. Sorry, let's say it as follows. We say that poisoned candy are those candy for which f is equal to some h from the finite set. Yes, I think this works. Yeah, it should work, but I will soon give another proof with a much better bound here. So it actually goes down exponentially fast. Let me check what I should say. 2 plus. Yes. Okay, so this is our first lemma. And so here is the definition. And then I propose this definition as like most simple definition for qualitative version. Let's, before we go to quantitative version, let's speak a bit more about all other possible definitions. So I don't know how I could change this probability in an easy way, but we can change the order. So we have a limit and 2 supremas here. So we could change it and have, for example, put, we can have supremum over, so let us take the most general definition, the generous definition, limit over n, supremum over h and h, then the same probability here. So if we use this, we allow the limit to depend on the probability, then almost every class is learnable on average. So it's not a useful definition. And so it follows from this lemma also. So when we fix P, no, not from this lemma. So, well, there exists like Borel-Cantelli lemma, maybe in statistic course it is used. And then it says that every probability converges. Okay, it's exercise, but it is optional exercise. Another one is if we flip the suprema. So if we use supremum h here and supremum over p here. And this is actually also an interesting definition. And so here we want that for each classifier, the sample complexity goes to 0, independent of input distribution. But we allow more, for example, it's in structural risk minimization. It actually happens when H is more complex. It's normal that we will use more data. So we can use this for bigger, such a definition for bigger complexity classes. Yes. Oh, and then there is an exercise. Let H be a function that predicts binary labels 0 and 1, for which there are most finitely many elements that map to 1. And then this definition, it will be learnable. So this limit will go to 0. This supremum limit will go to 0. But this class is not learnable according to this definition. So here H, let me write that. By this 0, 1, E is equal to small f, for which f minus 1 of 1. Okay. So if we take an input set x of size 2 and 1, okay, let's say x here is equal to natural numbers. So when we take a set S here of size n to n, then when we restrict classifiers from H to this set here, we can get all the classifiers when we restrict to a finite set. And since we have all classifiers, we know that this supremum is 1 minus the probability of picking an element from the training set. And so we can apply this lemma here. We know that this probability is at most 1/2 because we pick 2 n elements, twice the size of the training set. So when we substitute 1/2 here, we have always at least 1/4. And so we see that this supremum is always at least 1/4. So it's not learnable on average, this class. Okay. So this is about qualitative definition. And let us now speak about quantitative definition, which is the sample complexity. So in sample complexity, we will look at this part, and for a given epsilon, we want to know whether, whether the risk is at least epsilon. So there are two so note that here we have two probabilities. Okay, let me say it more clearly. So what we want, let me make some space. What we want now, two things from our learning algorithm. We want that the output classifier has small risk, and we wanted to produce, so we call classifier good if it has small risk, and we want this to happen with high probability. So note that it may happen that training set is not representative. We might have an input where all the functions agree. So we cannot, and usually we cannot exclude. So as soon as we have three classifiers, we cannot not exclude this to happen. So therefore, there is a parameter delta that controls probability that we have bad luck with training set, and probability epsilon that controls how good, how close to zero we want our risk to be. So sample complexity is, So I will denote it by, so for a class H, the sample complexity with parameters epsilon delta is the minimum size n of training set such that learner outputs FSH with risk at most epsilon with probability at least 1 minus delta. So this is definition in words. Thus, probability over S from Pm so I will use some notation. So I will write here for the risk, I will write it in short like this. So This is sample complexity. Okay. If H contains one classifier, then the same observation. If H is just one classifier, then sample complexity for all epsilon and delta is equal to 0, right? Okay. If H contains two classifiers that always differ, what is sample complexity? Yeah, 1, again for all epsilon and delta. But if H contains 3 elements, then sample complexity is at least logarithmic in 1 over delta. So the dilemma, or if H contains such classifiers that do not, so in all other cases that are not covered yet. So either 3 or there are 2, but they're not agreeing in everything. Then sample complexity epsilon delta is at least binary logarithm of 1 over delta, sorry, 1 over 2 delta. So how do you prove this? So if we restrict to deterministic learners, we don't need the 2. So let's do like this. So what we will do here, and so this is for every H, and so we assume that, let's say, size of H is equal to 3, because it's like annoying thing to say. So when we have 3 classifiers, there are always 3 different classifiers. That means that there must be 2 that agree on some input and disagree on other inputs, because we only have 2 labels. Okay, so now let us consider just a subset S, or let's call it X prime. And it's equal to, so let's assume that f of X equals g of X, and f of X prime differs from g of X prime. And so let us consider these 2 inputs and use uniform distribution over these 2. They each have probability 1/2. Okay, so now you understand how you get this logarithm. I need to specify what's epsilon. Where is it? So, of course, if epsilon is bigger than 1/2, we are good, because one of the 2 constant functions will work. So let us use exactly 1/2, the weakest. No, what I'm saying is, yeah, it's not so easy. I mean, even if it's bigger than 1/2, yeah, and if it's random, it works. Sorry, we need a little bit less. Anything less than 1/2, say 1/4. We need to put here. There is some error in the lecture notes. I will correct it. So when I wrote them, I didn't think about probabilistic classifier. So when we have 1/4, for example, so how will we get this? So it can happen that input set contains the point where f and g agrees. So let us say that we have input size, training set of size n, and we have uniform distribution. So with probability 2 to the minus n, learner has no information about the classifier, and so it must output some classifier. And the best thing it can do in this case is output a random one. Either G, F or G. And so it will be correct with probability 1/2, but with probability 1/2, it will make a mistake. Oh, sorry, and since I have strict inequality here, sorry, I'm wrong. This 1/2 does work. So then maximum, so then classifier is correct with probability 1/2. And so probability of classifier outputting, it's all very logical, right? If I keep explaining, you will get tired again. So should I continue explaining this example? No, because it's almost time and we have still have to speak about learning thresholds. Okay. So now let's go to a more interesting class, which is threshold classifiers. So we consider functions all the form. So here we have HT of x is equal to plus x bigger than t, and I forgot that x is real numbers, and y is equal to minus over y. H is the threshold. And now our lemma is that the question is what is sample complexity of this class? And it says that n of H threshold epsilon delta is equal to 1 over epsilon ln 1 over delta. So ln is natural logarithm. Okay. So we will use something technical, but something that we use already many times. We will say that 1 plus r is smaller than exponent of r in the proof. When we prove mistake bound, we first have to say what is the learner that we will use. Learner will choose a threshold to be the smallest value of positive label. So of positive input. So learner output classifier HT with minimum xi for which yi becomes okay. Yeah, and if there is no such label, then it will always output. If it does not exist, then output x always negative label. Okay. Let us use T for the true classifier. Let's use R for what is returned. Okay, and so now, so let's make a small picture. And so we have some positive outputs. And then the true classifier might be here, and then our training set can contain some negative output. So where are the inputs that are wrongly classified in this picture? They are precisely here. And so there is some critical interval here at some value S, so that S be the minimum value for which this region has probability at least epsilon. So we will define this number S, and then we can find the probability of the bad event in the definition. So probability. So let me write S explicitly. So S is equal to the minimum which is B of S at least epsilon. Okay, and then I claim that we have F S of H written on the if training set contains an input in this interval ST. So this is the main point of the proof. Oh, okay, it can happen that no such S exists. Right? It can happen that all this part has probability less than epsilon. Then no such S exists, but then we are good. Because regardless of so then we're good for sure, because we're only wrong in this interval TS. So F is in infinity, then we are good. So okay. So yes. Now key point. If we have a point in this interval in our training set, then clearly our classifier will make error less than epsilon. And if our classifier makes less than epsilon mistakes, we must have a point in this interval, because the only place where we can be wrong, we're never wrong on negative inputs. We're only wrong on positive inputs, and it's clear, right? So now to bound this probability here, we need to say that for this value of n, this probability is valid. But this is okay. So let us. So we have to look to the training set. Training set points are independently generated from Pn. So what's probability that first training point misses this interval? What can we say about this probability? So the probability that x1 is not in ST. So we know that this probability must be more than at least 1 minus epsilon. And so that hitting the interval is probability at least epsilon by definition. So this is probability at most 1 minus epsilon. Okay, this is for the first input, but we do it n times. So also know that 1 minus epsilon is smaller than exponent minus epsilon. So probability that S is disjoint from S is smaller than 1 minus epsilon to the power n, so they're independent events. And so this is smaller than exponent minus epsilon n. Okay, and now if we substitute this value for n, then we see that this is smaller than delta. So n equal this value from lemma. And then we have that this is smaller than delta. So n is equal to, so just multiply by epsilon. And then you get something that's bigger than ln 1 over delta. And then there is some minus sign left, so it's something bounded by that. So it's clear. Yeah, that means that this lemma is proven. Okay, what about time? So till 10:50, there are 10 minutes left. Then in the notes, there's one more proof. So for learning finite classes, and then we can do the quiz. Yes. So now the next one is proposition. If H is finite, then sample complexity is the same as this thing, but inside the logarithm there is the size of H. Lemma and H of epsilon delta is smaller than 1 over epsilon ln H over delta. So this is important for theoretical computer science, for example. There are many hypothesis classes from circuits, they're all finite, and this gives optimal bound. Okay, so for the proof, we have a few important definitions. So two definitions of classifier. A consistent classifier is a classifier that's always consistent with the training set. So given an input from training set, it outputs a label that appears in the training set. So in the agnostic setting, we can have conflicting labels. So then if both labels appear, it should be just one of these labels. But in our case, only in the realizable setting, only one appears. So then it must be consistent with true function. And the second one is proper learner. Proper learner is algorithm that always outputs some classifier from the hypothesis class. So the proper learner for hypothesis class is, yeah. So the previous algorithm actually was improper algorithm. So you remember why? It was a special case in the beginning. If the training set has no negative labels, then we output the always negative classifier, which was strictly spoken, not in the definition of threshold classifiers that I gave. Okay. And so before I prove this lemma, or I even call it proposition because it's kind of important, I prove a lemma for every proper consistent learner. So for every proper consistent learner, all P or all. And I said same of all classifiers for all hypothesis spaces, for all n, for all h and h, we can bound probability that such a learner makes a mistake. A probability that sorry for my notation I use of h and epsilon is at most and size h exponent minus epsilon. So we will prove this, and this implies this lemma. So we say that probability of outputting a high-risk classifier is at most this thing. So when we set this equal to delta, and then solve for n and round up to get integer, we get this bound. Okay, so all we have to do is prove this lemma. Okay, so let us first pretend that H contains only one element. I mean, we already know it is kind of obvious to prove it. Or it's also a bad idea. Let's say that. Okay, the proof is very short and I forgot it, so I will just give the one that's written here. So let us fix F inside H. And we fix it such that probability F not equal to H is bigger than epsilon. So now let us bound probability that F is consistent with the training set. But that same argument as before. So let us look to, so here let us fix everything here, everything. And now let us also fix hypothesis at H, or that would be a bad one. We can only output this classifier F if the training set is consistent. If the training set has just bad inputs where F and H agree. But this is unlikely to happen because F and H are likely to differ. And so let us look to probability that F of X equals H of X. So probability over generating the training set for all X and S. So what is X1, yeah, Xi equals Hi, or I equals from 1 till n. Probability that this happens for the first input is at least 1 minus epsilon, at most 1 minus epsilon. Probability that this happens for all n inputs is 1 minus epsilon to the power n, which is exponent minus n times epsilon. The same argument again. But this is just for a single F here. So we can apply the union bound and get this lemma. That's it, that's the proof. So actually we can use F minus 1 here. Do you see why? And so we know that always one function will have zero risk, the true function. And so this is all F and H with this, but it cannot be true for all classifiers in H. Because by definition, true classifier will always be, oh, I didn't write it. Yeah, but we only consider true classifiers inside the class because we're working in, how it's called again? Realizable setting. Okay. Yes, it means that we are finished for this lecture, except for the quiz. Now I didn't have time to write down questions, so let's invent them on the spot. So people at home, you can send me the answer on email. And let me write down some questions. Okay, question. Let me go through the notes. so that I can remember. Yeah. So you need to answer true or false. So first, consider the class H. So let's have binary labels y equals to 0 or 1. And let us consider class H consisting of all f, for which sum of f of xi is finite. So the class of all functions with finitely many ones. So
Uh,
x,
Can you please write bigger?
okay, I will write bigger. Okay, so is it learnable on is learnable on average? Then another one, true or false, that if h is at least 3, then and h epsilon delta is always bigger than 0. Or epsilon strictly smaller than 1. In which level? And delta smaller than 1. And let's do another one where we restrict it. So for people in the class, can you take a little paper and then write your name and 3 answers, true or false? And so here is the same question, but we have for epsilon smaller than 1/2 and delta smaller than 1. I'm sorry for I changed the question here. So epsilon delta and at least 2. So for all. Okay. And I will give you one question anyway for submitting. So then normally I ask 4 questions with 4 options, but since I forgot my questions now, they're easy questions. I mean, not so easy questions, but so that's why I give +1 and only 2 options. So so if you do random guessing and submit something, you have at least half of the mark. Okay, and just you need to send it's like 2 minutes time of thinking, and then we will stop.
Can I also send you like a message of pen and paper?
Yeah. So, but can you get her? Yeah. So you have paper?
Where we can find your email?
Yeah, sorry, you need to send to my email. So, B. Bowens. And just write it in the subject line, so TTTF, so and write SLT in the subject. So normally there will be a grader, but now I didn't do it. So for example, true, 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 or true, true, false, so your answer here. So just by blanks here. I mean, now it doesn't matter much, but normally it gets graded automatically. At gmail.com. Let me write it. Okay, so you need to answer soon in a few seconds. Okay, so 20 seconds. There are no emails. So you need to email now. Okay, and let's go over the answers. So yeah, you need to send it now because I will tell the answers, or I can switch off Zoom. Then thank you. And then so the first one is true. I just said it literally in the lecture. It's false because this limit, because if we look on a finite set large enough, then we have the set of all functions. So any finite set, so this is false. Then this one is false because we have delta bigger than 1/2. So we can now put one of the two constant functions, and one of them will have risk small, at most 1/2. But here it should be true because the trick doesn't work, and if delta oh, but the bound was 2 divided by delta. Okay, I need to check carefully because I should have taken 1/4 here to be true. So I will count both true because I gave the proof for deterministic learner algorithms. But and so depending on what you okay, so you get 2 for free because it's the first quiz, and yeah. Okay, so see you next week, and then